Welcome to Calculus-Based Physics. Today will be review, but also you'll be learning some new things that I haven't taught you yet. I haven't focused on mainly the calculus portion of the physics stuff because I wanted y'all to get the physical concepts first. A student asked me before spring break, when are we going to do calculus-based physics? Well, I guess the answer is today. Today's topic is the drag or variable resistance force. Drag is basically a word that means resistance to motion caused by forcing an object to go through a fluid. Now, fluid can be a gas or a liquid. What's interesting about this force is that it's directly proportional in some form or another to how fast the object is trying to get through that medium. So take, for example, the airplane you can see on the bottom right. That airplane is trying to go through the sky. But in the sky is air. And the faster that airplane is going to try to get through that air, the more that air is going to push back on that airplane. So that's why we have functions like this, which basically tell you the relationship. The drag force is equal to some constant times the velocity of the airplane. And in some scenarios, the drag force is equal to times some constant times the velocity squared. This function depends on what material it is, or if it's air or liquid. Whatever it is, the Physics C exam will give you this function in the question. Okay, these are just examples. Before we go into the specifics of the drag force, we need to review Newton's laws. Okay, we need to refresh ourselves on the meanings behind the free body diagrams and the difference between equilibrium and net force. So take a helicopter, okay? Now, let's say the helicopter is in a vacuum on Earth. So what does Newton's first law say? Well, obviously, on the helicopter are two forces. The weight is trying to pull down on the helicopter, and the propellers are trying to push up on the helicopter. Now, if those forces equal each other, that's called equilibrium. Now, this is the misconception. Some people think that because things are in equilibrium, it must mean they're not moving. That's not true. Newton's first law says that if the forces are in equilibrium, it means there's no acceleration. It means there's no change. So it could be at rest, or it could be at a constant velocity. But here's the thing about free body diagrams. It never tells you what direction the object is going. Now, what is Newton's second law? Well, we have weight pulling down, but let's say the force applied is less than the weight. Now we have what's known as an unbalanced force. And when you have an unbalanced force, you have to use F equals ma. So I like to pick the winning direction, and I do the weight subtracted by the applied force. And that difference will tell you how much the object is accelerating. Let's talk about falling from rest with drag. Okay, how do we approach a question where something is falling, but there is actually air resistance? So a perfect example of this would be a falling leaf. A leaf is going to have considerable air resistance pushing back on it. So how does the motion of a leaf happen when it falls? Well, the moment it leaves the tree, it's in free fall because the only force acting upon the leaf is gravity and its weight. So it's at rest, but now the earth is pulling on it, and so its acceleration is gravity. And this is at the exact moment it leaves, pun intended. But now, as it starts to fall and get a little faster because of gravity, not only is the weight pulling down on it, but there's going to be some air resistance pushing back on it. Now that the leaf is still moving, but now it's accelerating at a smaller rate than gravity. Eventually, the leaf will reach what's known as a terminal velocity, and that occurs when the weight force equals the drag force. And when those forces equal each other, once again, it doesn't mean that the leaf stopped moving. It just means that the leaf is moving at a constant velocity. It's no longer accelerating, but it is moving. And there are two forces acting on it. And this is true for anything falling through the sky. A skydiver jumps out of an airplane is going to start to feel the force of the air push against him more and more as he gets faster. And there's a point in the skydive where he's falling, or she, at a constant rate toward the ground. I want to take us back to 1975 to an AP Physics C exam question. It says that a sphere of mass m is released from rest from a very tall height. As it falls, the air exerts a retarding drag force on the sphere that is proportional to the sphere's velocity, and they give you the function. The drag equals some constant times the velocity. And then it says neglect the buoyancy force of the air. Up is the positive direction. So part A of the question is basically drawing free body diagrams. On the free body diagram on the left, it wants the forces acting on the sphere just right after it's been released. And on the one on the right, they want you to draw a free body diagram of when it reaches terminal velocity. So we just went through this with the leaf. The moment it starts to fall, there will be a small drag force caused by the air. And the reason why it's small is because the leaf is hardly moving. And then when it reaches its terminal velocity, we know that the drag force and the weight are in equilibrium. I want to note that on both free body diagrams, I had to draw the arrow of the weight to be the same exact length because the weight of the object did not change. The only thing that's changing is the drag force. Also, they would have accepted you not drawing drag force at all on the first free body diagram because the force might be so small that you can barely even see it. The split second it's released. Now part B asks you to determine the terminal velocity of the sphere. Well, to do that, we have to look at the second free body diagram that we drew. You have to know that when it reaches the terminal velocity, all that means is that the drag has equaled the weight. And so I can apply Newton's first law. The object's moving at a constant velocity, therefore the drag equals the weight. The drag force is the same thing as kV. And then I solve for, and I get that the velocity is the weight divided by that constant. This is probably the easiest and most simple calculation that you'll ever do on a physics exam. All right, so this wasn't actually part C on the exam. I just added this one, the review dimensional analysis. But the question asks, what are the base units of constant K? To ensure that it's correct dimensional analysis. Because if this equation is true, drag is in newtons, velocity is in meters per second, what must K be? Well, let's look at the calculations we did in part B. And I'm going to go down to that second equation because it looks kind of easy to deal with here. Because it developed an expression that said kV equals mg. Well, knowing what the units are, whatever K is, it's being multiplied by meters per second. And that has to equal a kilogram times a meter per second squared if what I wrote here is true. And it is true. And I can see pretty easily that in the numerator, I'm going to need a kilogram. And I'm going to need one more second in the bottom of the denominator to make it second squared. So therefore, K must be kilograms per second. Now, if they ever ask you this on the exam, they probably would give you full credit for that. However, what they mean you to write as your final answer is it's a unit of mass divided by some unit of time. Let's go to the final part of the question. On this part of the question, they want you to draw an acceleration time graph, a velocity time graph, and a position time graph of this sphere that's falling. And at this time, I would like you to pause the YouTube video and try it on your own before I answer it, and then compare your answer with mine and see how many points you would have got. So please pause the YouTube video now. Okay, so I'm going to go over the answer. So we must remember that the question told us to define up as positive y. Okay, now we know that it started at a very tall height. So I'm going to draw the object when it starts to fall. It's some height above the ground, and it only has one force acting on it the moment it leaves, and that's gravity. So its position is at point H. It's not moving, it's at rest for that split second. And its acceleration is negative g because gravity is pointing down. So I know my initial positions on all my graphs. Now I'm going to think about later in the object's motion. I know as it falls that there's going to be some time or some period of time where it's going to be at a terminal velocity. Okay, so that's when the object's in equilibrium, and I drew it falling. Okay, and the forces are in equilibrium, so I know that there's going to be no acceleration for that period of time. Okay, so I'm going to draw a line that's pretty much hugging the zero. Now it's moving at a constant velocity, okay, and that's moving down, so it's going to be a negative velocity. But that velocity remains. That's why I drew a line saying that the velocity is not changing. And because it's falling, it's still falling, it's just falling at some constant velocity. So its position is changing with a constant slope going downward as it approaches the ground. And now let me consider the time between the beginning and the terminal velocity. The forces are not in equilibrium. However, it's still getting faster, but that acceleration is going to be something less than g. So my acceleration graph, the acceleration of the object is going to decrease and decrease until it finally reaches zero. Now let me fill in my velocity time graph. I draw a line that's getting faster and faster. It's getting to be a higher and higher negative number, but the initial slope of it has to be negative gravity. And the final one is to draw the position time graph. Now here's a little trick. To know how to draw the shape of this, always look back to the acceleration graph. If my accelerations are negative, that means that my position time graph is going to be concave down. And concave down is a fraction. So I'm going to draw a concave down curve. And that's it. Those are the acceleration time, velocity time, and position time graphs. So in your notes, I would draw the correct answer and compare it to your answer. Now there were like 9 points given. There would have been a point for each starting position. There would have been a point for drawing each part of the terminal velocity side correctly. And there would have been points for the concavities of each line. Now it's time to get into calculus. Okay? I checked, and it seems that this year on your AP Calculus A, B, and BC exams, you have to learn a process known as the separation of variables. Okay, you should have learned this already, but if you haven't, I'm going to go through the process with you. Okay, let's go to a question from 2010, exactly a decade ago. Except in this example, the air resistance is not on an object that's falling, it's on an object that's being pushed to the right. And in the example, there's a constant force, it could be a rope, it could be something, it's a force applied, pulling it to the right. And the object has a velocity going to the right. It says that there's no friction, but there is air resistance, and they gave us the drag function. In part A, once again, they want us to draw a free body diagram. At this point, I'd ask you to pause the video and try to draw the free body diagram on your own of all the forces and only forces that are acting on the object. Okay, let's see what they are. These should be the forces that you drew. It has a force applied, pulling it to the right. It has a drag force pulling it on the left. I drew the drag force smaller than the applied force, assuming that it hasn't reached its terminal velocity. They did not say draw a free body diagram of the object once it reached its terminal velocity. It just said draw a free body diagram of the scenario. And so I had to draw the more generic scenario where the drag force is less than the applied force. And I think maybe some of y'all forgot to draw the vertical forces. But object has a normal force and it has weight. And those forces are in equilibrium because the box is obviously not accelerating into the ground or off the surface. So those forces have to be in equilibrium. Okay, let's go over part B. It says, write but do not solve a differential equation that could be used to determine the speed v of the box as a function of time. You're probably thinking, what is a differential equation? Sounds scary, but it's actually easier than you think. So let's take a look at that free body diagram that we just drew. Now, the velocity of the object has happened horizontally. So therefore, I have to do Newton's second law on the x-axis. Now, I'm going to pick the right as the winning direction. And also, the velocity of the object is to the right, so I'm going to call right positive. And therefore, the net force is going to be the applied force minus the drag force. And that has to equal ma. Now, here, I have to plug in what the drag force is. So the drag force is defined as kV. So I plug that into the equation. And what's interesting about this equation is that we have the acceleration of the object depending on the velocity of the object. But if you think about it, the velocity of the object depends on how much it's accelerated. So it's kind of like we have some sort of loop going on with this equation. So most of y'all know the definition of acceleration is change in velocity over change in time. But you can only use that formula when the acceleration is uniform and constant, or if you're planning on calculating an average acceleration. In calculus, we like to take those deltas and change them to little d's, okay? So really, that equation actually says that acceleration is the derivative of velocity in respect to time. And so what I'm going to do is I'm going to plug that into A in my equation over there. And actually now I have answered part B. I have just created a differential equation. And what makes it a differential equation? A differential equation, if I rewrite it and I color things differently, shows that the velocity and the derivative of velocity are in the same expression. Which means that there's some sort of answer that has to satisfy this equation. What function can you think of exist wherein the derivative of the function in some way could equal the original function. We'll get to that one a little later. Okay, part C says determine the magnitude of the terminal velocity of the box. For this, I draw a new free body diagram. We know by now that terminal velocity happens when the applied force equals the drag force. So I'm applying Newton's first law. Now here's another way of doing that. I'm saying, hey, the summation of forces on x equals 0. It's no longer accelerating. That means the applied force minus the drag force equals 0. In other words, Fa equals d. Now you could have started there as long as you wrote on the side equilibrium. Okay, to get the points for the AP Physics C exam, you need to write formulas down. And you can skip to this step as long as you write the word equilibrium next to it. And then I plug in the function for d, and I solve for velocity, and it's kind of like the previous question. All right, I've sped through that one because we already did that. Now it's time to get to the real calculus of Physics C. Right there. And derive the equation for speed v. In other words, we're looking for the function v that would satisfy this differential equation. So you have to know this for your calculus class, both AB and BC students, and it's still being tested, I checked. It's called the separation of variables. Separation of variables occurs when you put all of the velocities on one side and the time on the other side. I basically took this derivative here and I split it to both sides of the equation. And the reason why we separated both, and that's why they call it the separation of variables, is so that we could take an integral on both sides. And I want a generic function, so I'm going to do that function from time 0 all the way to any given time. And the same thing over here on the right for velocity. The object was at rest, and I'm integrating to some random point where it's going faster than rest. Now the integral on the right, you should notice something. We have a differential of v on the numerator and the function v in the denominator. Most of y'all know that the integral of 1 over x dx is basically the ln function. Well, I call it the ln function, but natural logarithm. Okay. Now the left integral is easier than the right integral. That's just going to be time over mass. And now let's do the right side of the integral. It's going to be the ln function. Now, if you don't understand how I got this step to this step, you might have to do u substitution. I kind of know how to solve these integrals intuitively. I just think, hey, if I derived this function right here, what would it be? So I always look backwards thinking, hey, would that derivative be true? So we have to evaluate the integral from 0 to v. So that's basically subtracting the function. And subtracting logarithms, you have to use your logarithm rules. But subtracting a logarithm is the same thing as dividing the contents of one logarithm. I'm going to multiply negative k on both sides. And now I can solve for v. Remember, it wants a function for v, and I'm solving for v. So I'm solving for something that's inside of the logarithm. I'm going to have to use a log rule or convert it to e form. And now I need to solve for v. And that's our final answer. So from there, you can see that the functions that the derivatives equal its original is some form of e. Also, I want to note that in the exponent of the e is a negative exponent, which means it's a decay function. And why is that important to know? It just means that the velocity is decaying, okay? It's still getting faster and faster and faster, but the rate at which it gets faster is always getting smaller and smaller. And note, if you take the limit of this function of time going to infinity, you will get the terminal velocity as your final answer. Okay, well, that was a long video and I bet overwhelming, but I would like to say one thing here. You do not waste valuable time on the AP Physics C exam going through the full calculation. You will get the majority of the points probably by reaching this point right here, okay? If you want to save your time on the exam, stop there, go to other questions, and if you have remaining time, come back and finish it. All right, guys. I'm going to give you all an assignment. It's based off of this video, and good luck. Hopefully this wasn't too overwhelming for you guys. But this is how you solve drag, and welcome to calculus-based physics.